take a quick look here. Okay. So quickly, upper cases, these are case sensitive here as it goes. You might want it, for example, somebody asked about case sensitivity. You might not want your word stuff to be case sensitive. Well, how could you remove case sensitivity? Actually, the Natural Language Toolkit has some simple tools to do that, but you could also do it yourself. Okay, let's look at, before we move on to our next example problem, I'll take a little bit of a breather here and mention a separate topic that I just wanted to work in here somewhere, which is optimizations, because performance for some of you will be important. For many of you, it'll always be good enough. Spark's pretty smart at doing a lot of things, and you won't worry about it. For some of you, you may move on to things that are data sets that are so huge, or environments. Maybe you're in an enterprise environment where you're running these things on every hour to get an analysis to send to somebody's dashboard or whatever, and you care about performance. If you care about performance, Spark does have a number of ways to affect it, to analyze it and affect it. So I'll very quickly just whip through those. And I say quickly here because I just want to introduce you to the topic. If you have specific questions, you can ask me, later offline. And if you want to dive into these topics more deeply, their Spark documentation is pretty good, but many of you may never use these, so that's why I'm going to be quick. One of the things that Spark does automatically for us is try to juggle things between disk and RAM. Keeping things in RAM is obviously much faster to use when you're doing analysis and manipulating the data than if it's on disk. But disk, of course, has a lot more space than RAM. Well, Spark does all of that juggling for you, and that may be all you ever care about. However, you may want to start to influence that in some way. You might be a little bit smarter than its algorithms in terms of knowing when your data should stick around. You might do some analysis on some data and know that you're going to use this again later with a different RDD, and so maybe you'd like it to hang around. And you can give these kind of preferences to Spark with persistence directives. So we can see in this case here, we have an RDD, Stanford Lines RDD, and we think we're going to use it later, so we'd like it to hang around. We can suggest to Spark that it keep this in memory and disk. It's got different storage levels that we could suggest to it. And it will override these. If it runs out of memory, it'll override them, so you don't have to worry about, you have to calculate how much memory you have and everything else. These are only suggestions, but they are suggestions that it will give precedence to over its own algorithms as to when it thinks things should be moved back to disk or when they're stale and can be disregarded and purged completely. In a similar vein, partitions, where your data is actually distributed behind the scenes, behind that curtain across the disks, is something that Spark tries to do with a pretty intelligent, in an intelligent fashion with its own algorithms, and then by and large does a good job of that. However, you may know something about the way your data associates with one RDD associates with another RDD, and ways you combine them later on, and you might be a little bit smarter than Spark because of your own knowledge of your applications and your data. If so, you can define your own partitioning scheme and tell it how to group things together. At another level, you might want to actually work and think in terms of parallel programming. I keep alluding to the fact this is all parallel behind the scenes. Some of you that are comfortable with parallel programming may actually want to think more about, I'm actually using these parallel resources. If you want to dive down to that level and write things and think about how variables and data can be distributed in parallel and work on things on an element by element basis on different cores, you can do that. It has some high level features that allow you to do that parallel stuff behind the scenes, accumulators and broadcast variables. And for those of you that are comfortable with parallel programming, these functionalities should seem pretty natural. They correspond to the kind of things you naturally do in parallel programming elsewhere. For those of you that don't ever want to dig behind the scenes, you don't ever have to worry about this stuff. And of course, maybe the most important thing about performance is, do you have a handle on whether you do have decent performance, or whether there's a lot to squeeze out of it, or whether something really expensive is going on. And that means that you'd like to have some way of actually monitoring the performance. And Spark has a nice web interface to allow you to see exactly what's going on with its different RDDs and different transforms it's doing, and to see where the time is being spent, and to see if it's what you think is going on. And so there's a web interface that you can use to get to things. And it's also got a configuration class with lots and lots of options in there that you can tweak and try to adjust and configure things and have it be a little bit smarter. So many of you may never care about this and assume that things are good enough, and they may well be good enough, but some of you may want to dive into performance. And it's always nice to know that at least the system's been built with that in mind, and you don't have to go and start messing with source code and recompiling, building your own Spark installation because you decided that, because something isn't configured for your purposes. So Spark has those considerations built in, and that's all I'll say about it. because many of you will find that its default behavior is very good. Now, IO formats is something that we have a number of questions about already, and I can't blame you because we've only been working with text so far. And the question is, what about when the data inputs do get more sophisticated than just our text file command? And the answer is that Spark is very comfortable with dealing with much more sophisticated data inputs. So text and comma separated variable types of things, we've already, sucked data in with our text thing, but we could load data in, and we'll see an example of this at the very end today with when we look into data frames. We can read in data from SQL databases directly. We don't have to write. You might think that for in the past, if you've got a database and you want to read something into some other post-processing system, it was up to you to spit data out in the right format and do the right manipulations so that it fits into the next piece of your pipeline. Spark eliminates an awful lot of that. It allows you to say, okay, I'm using a Mongo database to store this table, and I need to bring some of that data in to use in my analysis. And maybe I want to bring some data in from another database. I'm going to combine. Spark allows you to just import that data with just RDD input commands that convert the data into the appropriate format, usually a data frame or a table type format. We'll get to that in a little bit, but it sucks in the data directly in these native formats. You do not have to go and do this intermediate processing. That is a wonderful thing. That's just a painful bunch of stuff nobody wants to do and maintain. And it has a wide variety of things. This is by no means a comprehensive list, but it gives you some idea of some of the diversity here. So Hive is, for example, an older Hadoop-driven database format that it's become very popular as an exchange that can read that right in, as well as popular databases, JDBC-based things, Cassandra. I mean, there's lots of things, and compressed files as well. You can read it in a compressed file, boom, directly in. So this is some pretty neat, powerful stuff. And it can also interface directly with a number of file systems. I've mentioned that HDFS using a Hadoop file system is kind of the behind-the-scenes file system is very popular configuration because HDFS is a nice parallel distributed file system with some good characteristics. But you can go and install this on your local laptop, and it'll just use your boring single hard drive or SSD that you got sitting in your laptop. It's not a very interesting file system or high-performance one, but Spark's happy to do the best it can there. On bridges, you can connect up with Lustre, which is a very high-performance, massively parallel file system. You can also connect directly up with cloudy-based things like Amazon instances, Azure instances. It'll connect directly to those. So that's a very powerful thing to be able to do, is to be able to use other large-scale, high-performance file systems natively. And that's all set up so that when you start, that Spark context we talked about earlier, when you start Spark up, after you've configured it, your system administrator or you or whoever has configured Spark, when you start up, that just magically becomes your Spark context that you use with all of your operations. So you don't have to go and mess with any of the code that we're working on today or the codes that you might develop to adapt them to these different file systems. That will all just happen through the Spark context when you configure things. In line with that, besides just file systems, you also might want to read things in a streaming fashion. I mentioned earlier that streaming data is becoming a bigger and bigger thing. As a matter of fact, I think on this slide here, I have a number that I just saw recently, a number that 15% of the global data sphere, which is in some sense the amount of data that's out there floating around, is currently real time. Data that is happening in real time. And that number is growing as a percentage too, is growing. I mean, the trend is definitely up. There's a lot of streaming data out there. And if you were to do this stuff with streaming data yourself, you might think it's easy to do, to adapt any normal static database or file system or data management thing to do streaming data. I'll just read in chunks of data and I'll keep doing that all the time. Only in the real world, you have a lot of issues like recovery from failures and timeouts. This happens all the time with things, right? I mean, my audio broke up a little bit here apparently. So, I mean, who knows why? We'll never figure it out, but you want a system that's robust enough to deal with that kind of stuff. Load balancing. We do have this parallel machinery behind the scenes, but the data stream that's coming in may ramp up, may ramp down. Your resources may get busy or whatever, or have idle time. Load balancing is not a trivial thing to do. You don't want to write your own stuff to deal with that. You're going to have streaming data come in, and most likely you're going to want to do analysis that also involves some static database that exists. And you're going to compare things between the two. And you might want to compare them with things that involve machine learning and SQL. Spark allows you to pull all these pieces together in one framework without you having to write all that glue. And again, in this case, that glue would not be trivial. So that's all I'll say about streaming. But for those of you that is part of your reality, rest assured there's a lot more behind there. What we are going to spend a lot of time on, because I think it's primary focus of this workshop is our machine learning aspects of Spark. And Spark has a machine learning library, mlib, that rolls in a lot of classic machine learning algorithms. We're not even going to have time to touch on a large number of them, but we'll get into some of the basic ones here. It includes all the basic data types and statistics kind of stuff that you would expect to have. Classification stuff. So for some of you, these terms will be brand new. We're going to explore some of these things over the next day and a half. Some of them we will not have time to, but for those of you that are already heavily involved in machine learning, these are all fundamental pieces that you'll find yourself wanting to use or potentially wanting to use. And Spark has all these built into mlib. Tomorrow, for example, or even today, we'll touch today on the end of the day on principal component analysis. Tomorrow we'll touch on SVD. And we'll get into some of the algorithms like stochastic gradient descent. These are all built into Spark. What we're going to do first, though, is our next exercise is clustering. And clustering is an extremely important thing in machine learning. Now, to use mlib as we go through this, it is very straightforward to just import it. But because it is large and sophisticated, has lots of pieces to it, you probably want to have the web browser open when you're using mlib to its documentation, which is pretty good. It's got an excellent reference document here. So Spark is an Apache project. They do a pretty good job with their high-profile stuff of documenting it, and indeed that's the case here. And so I suggest that you have this open as you're doing your Spark work. But let's talk about clustering a little bit because it's a really, really important fundamental part of machine learning. And if you're new to machine learning, you might think that it's just a particular thing good for some obvious problems instead of the fact that it is widely usable across maybe, I'll make the statement, maybe most machine learning problems can be addressed with a clustering technique and should be thought of maybe in some clustering sense. And we'll see that as we go along here today and tomorrow. But let's jump into it with the most obvious kind of problems, which are you got a bunch of data that's obviously clustered. So let's say we've got, for example, our coin sorting problem. We were just visiting some random countries and we're pulling coins out of our pockets, and I pull out some coins here. I was using in Uruguay, and I dump them on a table, and without knowing anything about the coins, or I've forgotten completely what they are, I sort them by their size and their weight, and they group themselves like this. Well, without knowing anything about the coins, their denominations or anything else, I can kind of tell how many denominations there are at least by their clustering. I might not know their values, but I can at least see by their clustering how many different types of coins I have. So this type of clustering problem is used whenever you don't know a lot about your data or what's called unsupervised learning. We don't have anybody to help us learn things. We don't have any labeled example data sets. We're just starting from scratch. So we can't read any of the language on these coins, but we can already infer some important stuff about the data set, at least how many different denominations there are. And that's what clustering allows us to do. And we'll see this applies to a surprising number of problems. But first, let's look at how we do clustering even on this simple type of problem here. And right away, if you're new to this, again, it might seem easy to do because you might think that clusters look a lot like this, like our coins do, a bunch of stuff spread out in our space here, size and weight. Well, first of all, our problems a lot of times won't just be two-dimensional. We'll get into that later. Our problems can often be much higher dimensional and we can't even visualize them properly. But even in a two-dimensional world, do you want to write an algorithm that figures out how many clusters there are here? Maybe it's not quite as easy as you think to write a clustering algorithm, right? More importantly, data usually looks a lot more like this. This is what clustering data looks like most of the time for most data sets. How many clusters are here? I mean, that is debatable, right? Even us as humans being able to stare at this, how many clusters are there here? This is the situation we usually have. And we don't have often the ability to even visualize the data because it might be a 12-dimensional data set. It very often will be. And we can't even visualize it. So we can't even begin to do this. So we better get good at using our clustering tools appropriately so that we can do this blind, so to speak, and figure out how many clusters there are in something like this in 12 dimensions. But we're going to start out with a problem that we can visualize. We're going to start out with 5,000 2D points. So it might look something like this, or it might look like this, but let's try to see if we can tease some structure out of it with our clustering tools. without actually looking at the data set until the very end when we'll peak. Okay, if you want to play along in real time, you know how to do it. Same thing we've been doing. I would suggest that you don't play along with me and you wait until afterwards to do this, because you'll be able to pay more attention, because I'm not going to slow down a whole lot. And since I can't hear your questions, I'm not going to keep diverting over to the chat channel. So we're gonna work through this slowly. Probably you just want to pay attention and work on it and play with it and do variations later. But if you want to play along in real time, again, you know already how to start things up. When you're in login node, type interact. When you're on your compute node, node Spark, type PySpark. You might already still be sitting there from the Shakespeare exercise, so you're good to go. Okay, let's do the basic things we can do in Spark. First thing we want to do is read our text file in. It happens to be a human readable text file. If you pull it up in your editor, you'll notice that it's 5,000 XY points. So it's a nice human readable file. We'll read it in with this text file command, and there we are. Now, once we read it in, we realize that it's not actually numbers, it's text, it's ASCII strings, and we need to turn these into a couple of integers, because that's what our machine learning clustering algorithm expects. It expects us to feed it a bunch of points, real numbers or integers, certainly not a bunch of text strings. And so we need to convert it. And this is where, once again, Spark shines, because processing data is the kind of thing, and cleaning up data is the kind of thing it's really good at scale and in a convenient way. So let's do that here, a little bit of massaging our data. This seems terribly mundane, but realize that this right here applies to terabyte-sized data sets, and also these kind of tools apply when your data sets have lots of mysterious and weird noise, and big data sets always have that. They always have anomalous things that will crash your processing down line if you don't clean your data set up. And there's no better way to clean up a data set than with Spark tools like this, a large data set at least. Okay, so we read our points in. I did a quick take here. I counted them to make sure that I did the right. We got 5,000 points. That sounds right. And I take a look at them and I see that they're these Unicode strings. Okay, that looks right. Everything looks right, only I need to turn these into numbers. Okay, simple enough. I split them into two pieces with the split command that we know. Let me take a look at that and make sure I'm doing the right thing. I look at that and go, okay, that's right. Now I got two strings for each point. That's a step in the right direction. Now I just need to turn them all into integers. So now I do a map and I turn each one of these strings into an integer. Very good. I'm in good shape here. I've got a bunch of pairs of integers in my RDD now, which is what the following algorithm, the clustering algorithm, is going to want. It wants pairs of numbers. So you can see this text pre-processing and manipulation and whatnot is pretty convenient. Okay, now let's do the actual interesting K-means machine learning stuff, which means we import the mlib library, very straightforward to do. We end up with this, hopefully your browser next to you, showing you all these different things that are in the mlib library. And if we pull up K-means, which is what we're about to use here, the K-means clustering algorithm, we see all the parameters that it takes. And the K-means clustering algorithm is probably the most, well, undoubtedly the most popular way to do clustering for a variety of reasons. It's well understood and works with, pretty complex and muddy and ugly data sets. It parallelizes very well, which is very important in the modern world. That it can run on GPUs, and it can run on large distributed clusters and things like this. So K-means is nice and powerful because it parallelizes. But it has a number of parameters to it here, which we'll need to understand if we're going to use it appropriately. The first parameter is the data set that we're going to dump into it, an RDD. No big deal. We've got an RDD ready to go here. RDD3 looks like it's a bunch of data points that we're ready to feed it. The next parameter here is one, though, that might catch you off guard a little bit. The number of clusters to create. Well, we'll come back to that. Let me look at quickly a couple of, well, no, we'll start here. We'll look at this one, the number of clusters to create, because this is the most, for people, the most surprising parameter, in that isn't the clustering algorithm supposed to tell us how many clusters there are? Isn't that the idea? What do you mean the number of clusters to create? And the answer is that clustering is a tricky problem. As if I go back to, to this slide here, clustering looks like this. Expecting our clustering algorithm to tell us how many clusters there are on this is asking an awful lot of it. Since you probably can't, you and I would disagree with how many clusters there are here if we had to start from scratch, right? So what clustering algorithms in the real world of real messy data do, because they're not dealing with this all the time. In that case, it'd be easy to tell, say, how many clusters are there. Because we deal with data like this, what we do instead with clustering is we ask the clustering algorithm to find 10 clusters here. And it does its best job of finding 10 clusters. And we can look at the total error, how well the clusters fit, by some metric, some total error number. And we'll define that very straightforward fashion. And it gives us an error. And we can say, okay, now let's look for 12 clusters here. Does that fit better or worse than 10 clusters? So what we do is we try to find different types, different numbers of clusters, and we see which ones fit best. And again, that might seem not ideal. I want my clustering algorithm to just tell me where the clusters are, but that's the reality of real clustering in the real world. Is the clustering algorithms have to, we tell it how many clusters to find, they do their best finding it, and then we have to look at how well that fits. So that's exactly what we're going to do here, and that's why we have to tell it how many clusters to find right here. So that's part of the challenge of clustering. Okay, what else is there going on here that we have to tell it? It has a random number involved here. And this is another principle that we're going to see crop up again today and tomorrow endlessly, is these random numbers, these seeds seem to be involved with all of our machine learning, that we've got some random initialization thing. Even when it doesn't seem obvious, like finding clusters, where's the random part of finding clusters? Why is there a random seed that we have to do? And the answer is, for this algorithm, we'll see that this applies in different forms to almost everything in machine learning. There is a random element here. With clustering, when we even start to try to assemble clusters, when Kmeans starts to try to figure out how to draw circles around clusters, basically, it has to pick some place to start. And that starting point for any given algorithm might have some effect on the answer. Indeed, it does. If you start trying to draw clusters up here, you might pick a cluster out here, then the next cluster that you try to assemble might have some points. So clustering has a little bit of a non-deterministic element to it, as do most machine learning algorithms. And you hope it's not a major effect, but it's one that you definitely want to pay attention to. And so we can't just ignore that. Instead, our seed here will basically correspond to how it begins assembling these clusters. And the good thing about having a handle on your seed, paying attention to the seed here, is that we can set it to something and control it. So we can say, if the seed is always set equal to 1 to start with, it's always going to start assembling the clusters in the same way. And if we change it to 10, it's going to start somewhere else. And we can at least see if we're real sensitive to that. If you're sensitive to having a different random seed, then your answer is probably not really solid. You know, you hope you get the same number of clusters regardless of where you start. So you want to have some control over that. And we'll come back to that. We're going to keep seeing all these machine learning algorithms have these initialization seeds and things. And you want to pay attention. You hope that they're not important, but they're always there. So you want to make sure they're not important by occasionally changing it and seeing if it changes your answer. You hope it doesn't. Okay, let's take a look at what this error is that we use to decide if we're finding good clusters or not. And it turns out that our clustering algorithm is going to return to us as its value what it calls the cost in this case here, or the error, or the loss. These are terms that are pretty synonymous in machine learning, so get used to hearing all of them as you bounce around between different problems. Cost or error or loss, basically how far are we from, from what we think is some correct value. And the cost that we use for clustering is the distance. So we're going to end up with, say we have 4 clusters here for this point right here. We go with 4 clusters. Kmeans is going to do its best to draw 4 clusters around our data points. At this point, we still don't know what they look like, but it's going to draw 4 clusters. With those 4 clusters, how well they fit could be characterized by saying, how far is each point from the center of the cluster? A cluster really has a center point to it, right? Centroid. So we go and we take every point, how far is it from the center of that cluster? And if we have a good fit, most of the points are going to be close to the center of their clusters. If we have a bad fit, the points are going to be far away and it's going to have a high cost. So in other words, once again, to go back to this slide here, if we clustered this with, how many points are there? 1, 2, 3, 4, 5, 6, 7, 8, 9 points here. So if we clustered this with 9 points, each one of the points is going to be right on top of it and we'd have 0, right? Our error would be 0. But what if we clustered this with 8 points? Then somewhere we're going to have a cluster maybe that circles these 2 right here. And the cluster center might be in the middle. Now we're going to have some error because the points are going to be distance from the cluster center. So the cluster centers and how close they are to all the points are a good measure of error. And that's exactly what it is, just a geometrical distance of all the points from their assigned cluster center. So that's what our cost is. Now, you might say, well, we'd like to drive that error to 0. And here's the answer of why we would not like to drive it to 0. If we have, well, let me go back to the slide we were on. If we have 5,000 points and they are arranged in nice clusters, what happens if I ask for 5,000 clusters? My error is always going to be 0. Even though our 5,000 points might be in, say, 10 nice clusters, So we might really only have 10 nice clusters. Or maybe I'll suggest we have 15 nice clusters, because that's what this data here is about to suggest to us when we get onto it. But if I have 5,000 points and I say, find me 5,000 clusters, the error will always be 0, because it's going to put 1 cluster per point. Now, is that actually meaningful? It tells me nothing about my data. What I really care about is how many real groups are there out there. And the way that we have to determine that is we look at our error as it drops off as we try for more and more clusters. And at some point, we have our final drop off, and then it's pretty much close to 0. And it stays there until we asymptotically drive it to 0. So that tells us that we probably have, and we're done, we'll look at the data set, but we probably have here maybe 15 clusters. So that's my guess, is that we have 15 clusters here. We have the luxury of being able to look at this data set. But again, if this were a billion elements in 12 dimensions and the clusters were fuzzy, we're going to have to rely upon this to tell us the true answer. We're never going to be able to actually visualize it. So in this case, when the error finally goes to 0 with its or gets as close to 0 as it's going to get before it asymptotically trails off, I think we have 15 clusters. And again, we will keep driving to 0 more and more as we end up with more clusters, but maybe they're not doing anything more than assigning a cluster to each point. So here's how we're going to test this. Here's how we generated that previous graph, is we just ran our K-means model. We trained it on, and that's the term that we're going to find being used here in machine learning. We trained our model on this RDD for clusters from 1 to 30. We said, try to form 1 cluster and then print out the cost. Try to form 2 clusters and print out the cost. So that's how we generated this graph from the previous slide, is by looking for different cluster counts, we spit out this graph right here. And so I think that we have 15 clusters. We'll see. But this is the only code it took to generate that, as we kept running K-means on different numbers of clusters. Okay, here's the kind of data that I get out for this. This is what generated that graph that we looked at. Here's the total cost, and it starts out at 10 to the 14th. So these points are separated. These points are on like a 100,000 by 100,000 grid. So the numbers are pretty big. Not that the scale matters here. So we had, 8 trillion, was our cost here. And we can see if this, well, the graph shows it better than trying to read through all these numbers. But if we go through these numbers here, we can see the previous graph. We can see it kind of takes this dip down to 12 here, right at about 15. And then it stays low. So that's what leads me to believe, by looking at that graph, that we have about 15 clusters. But as I said, this stuff isn't entirely deterministic. Based on the random seed and where it started, maybe there's a little variation. So I better investigate this. Well, the nice thing with Spark, I'm sitting here in my interactive shell. I'm typing away right here, doing this in real time. This only takes a second. You're all going to try it yourselves. It only takes a couple seconds to do. So I'm doing this in real time. So I go, okay, let's do some experiments here. Let me run 10 experiments in a range from 12 to 18. I think there's about 15 clusters. So I'm going to investigate in this range of 12 to 18. I'm going to try 10 more trials, right? It's trivial. It's quick and easy for me to type this stuff up. I'm sitting in a Python shell. Let me try 10 more runs in the same region and make sure it's repeatable. And if I do that, I do find there is some variation here. It isn't entirely repeatable. I do get, one time it looks like there's 16 clusters. Now it looks like there's 15. Now it looks like there's 17. There's a little bit of variation here. So it looks like there could be anywhere from 15 to 17 clusters. So there is some variation. This shows very much how K-means really works in the real world with fuzzy data sets. But I think that 15 is as good as we're going to do. So I'm guessing that there's about 15 actual clusters here. So we're going to visualize this when we're done and see if that's true. But I also investigated and made sure there isn't wild variation here. And I could see that with the right clustering guess, it seems to get to 15 and can't do much better than that. And I could, of course, run 100 experiments or whatever if I were really paranoid very easily. Okay, now that I've got the clusters, I actually probably care about, to use the data, I care about their centers. So I'm going to do the same run of 10 experiments here over the same range. And whenever it finds a model whose cost is pretty low, less than this, trillion here, 10 trillion here, whatever it is, 10 to the 13, 10 trillion, I guess. Whenever it's got a cost that's less than this, print out the cluster centers so I can, see what some good guesses for cluster centers are. And the whole reason that I'm kind of stepping through this with you is to show that I can kind of just play around with this in real time. I'm getting to explore my data set in real time. And with 5,000 points, you can probably do this on your laptop in real time. It won't take that long. With millions of points in higher dimensional spaces, this is going to take a long time. And that's where it's wonderful to be working in Spark, because if it takes too long, I can just grab more compute nodes and scale up. Okay, if I do this experiment, I find out that once again here, I've got two two runs that come in here at less than 15 trillion, I guess it is, meters or whatever units you want to pick in cost. And here are the cluster centers for those. So these are my 15 clusters. These are the X and Y coordinates of my clusters, which is nice because now I can actually plot them out. And let's do that. Let's plot this against our real data since we have the luxury of doing that. So here at last is the data set we've been working with. We have the luxury of seeing it. These are our 5,000 points here in our 100,000 or our 1 million, I guess it is, by 1 million grid. So here's our 5,000 data points. So we can see these are pretty solid clusters, not too bad, but also not entirely unambiguous. We got to draw some circles here somewhere. And let's see what our cluster centers, the K-means found are. And here they are. Here are our 15 cluster centers. So I think we did a pretty good job of finding the actual cluster centers of our actual clusters. Okay, what about the runs that we're saying there were 16 clusters? Did it just go and put some wild point out there? No, 16 clusters basically looks like it more or less just found a cluster in here to space these out a little bit. Okay, that's not entirely crazy. I can believe there's another cluster here. These are really 3 clusters instead of 2. It's possible. So it wasn't crazy, but I do think our 15 was pretty much the optimal number. So this is how we do clustering in Spark. And again, there are clustering algorithms in scikit-learn, which you can put on your laptop, and you probably should. If you're interested in data science, it's always nice to have on your laptop, to have scikit-learn sitting there and use its clustering algorithm when you're working on small data sets and toy data sets. And at some point, when you import all of a sudden, like, as I said, right now we're running epidemiological data for COVID on bridges, you import a data set that's, all of a sudden now got hundreds of millions of things in it. Well, now your laptop isn't handling it anymore. Or even your laptop can handle it, but it takes 15 minutes to do each one of these analyses. That's not really interactive anymore, right? And I like to be able to play with the data interactively, at least when I'm investigating it initially. So now you can take and move into Spark, and when you're in Spark, you can do this. You can scale up as large as you need to handle the largest data sets and to be interactive. But again, K-means is something that you can plunk down on your laptop with scikit-learn and do just fine right there.
I have a question.
Okay. Question? No, I don't.
Is this variation coming from having different seed number when running 10 more K-means from 12 to 18?
Yes, the variation exactly is coming from having a different seed number. That's a good question. It's important for me to emphasize that. If we use the same seed over and over, we would have, so what we're seeing right here is the variation with different seed numbers. If we use the same seed, if we're not setting, you'll notice when the parameters that we give into K-means, I'm not setting the seed. If I set the seed equal to 1, these would all give me the same thing, and I wouldn't really be exploring it. But by not setting the seed, it's using a different seed every time, and I am seeing how I'm getting different clustering coming back from it. And it's important to understand that and make sure that you're not fooling yourself, that your clustering algorithm is repeatable to some degree. So you're seeing right here different seeds for each one of these runs, and that's why sometimes it even gets as many as 17 clusters. But we did enough exploration there that I was pretty confident there was 15. Maybe I could have run it 100 times to make sure it wasn't going to find 14 clusters. I don't think it was going to find 14 clusters out of this particular data set. So that's exactly right. The seed is what gives us some handle on how much certainty there is in this data set. And you can imagine if we ran this on that even fuzzier data set that we had back there, I kept going back to, that it would be even less certain that the seed would really matter a whole lot because the clusters are even fuzzier. And this is, again, not a clustering thing per se. Machine learning has an awful lot of this where something that sounds like it should be deterministic algorithm has a seed. As a matter of fact, I think every problem from here on out has a random seed involved in it. And again, it's going to seem surprising on some of them, but it's the nature of these kind of problems.
Are all the clusters the same size and or shape?
These clusters are definitely not the same shape, but they have a centroid and they have assigned to that. Each one of these points is assigned to a particular centroid. So they could have a different shape that's not circular, for example. Each point, K-means assigns each point to a centroid. And we can go back and actually we can ask for each point which centroid it's assigned to. So we're looking at the centers, but we're not labeling each one of the points. I could color code these. We'll do this later. I will actually later start to color code some things when the clusters get a little bit more sophisticated as a back end to doing some deep learning tomorrow. And so I could have colored, one cluster red and one cluster blue, and you could see which points are assigned to which cluster, which is interesting to see. But we just didn't jump that, that deep in yet.
Could you quickly explain the model line in your code? How do you get the centers?
Okay, I will do that. And I just noticed, I wondered why I wasn't seeing any of these questions here. This scroll is not working on my chat. It was not scrolling down. So I'm sorry. I thought there were no questions coming in, and now I see a bunch of them. I'm glad Steve is here. Okay, so model is the key. It's the key routine here. So it's a good one. Let me go back to the simplest version of it, like, yeah, maybe right here. So it's the key routine. So, and this is kind of nice in that this terminology applies across machine learning. So we'll see this tomorrow, even with TensorFlow, which is a very different system. Model basically stands for, basically your whole hypothesis, everything when you're done training, all of your data that consists of what you've learned is kind of hidden in your model. So model has the ability, we train K-means and it gives us back a model. It means at this point, the model contains all the information we've managed to learn. In this case, it means pretty much what the clusters are, which points belong to which cluster, and their costs. So that's all the information. So when we have a model, it has all the data we've learned, and now we can query that model for things it knows. In this case, we're going to ask it for the compute cost. Yeah, I think in the next slide, we ask it for the centers. And so the model you train a model, at that point, it knows things because it's been trained, and the things it knows, you can ask it for. So that's pretty much the way it works here, and it's going to work with the things that we're going to look at later and tomorrow. So think of the model as kind of the sum total of your knowledge that you've trained something to learn.
Any advantage of ML with PySpark than traditional sklearn?
Okay, that's a good question. I answered it before. I'll answer it again, and I'll probably answer it again before the day is out, which is that PySpark will scale up and sklearn will not. Sklearn, you're stuck on your laptop or your workstation, maybe if you install a powerful workstation. PySpark is parallel, will scale up. So I can take, if I run this code on my laptop with these 5,000 points, with scikit-learn, probably takes, I don't know, 10 seconds, 15 seconds. If I run this with 5 million points, now it's going to start taking many minutes. I run it on a workstation with some GPUs, that comes back down to 10 or 15 seconds. I need 5 billion points. Now all of a sudden I need to run this on bridges, on multiple nodes, maybe nodes with multiple GPUs. Bridges, for example, has nodes with 16 GPUs in it. Maybe that's what I need in order to get reasonable time. So what we find here is that scikit-learn and other kits as well are great on your laptop, maybe even great on a decent workstation, but definitely no good as we move up to, or not scalable at all. It's not like they're kind of scalable, they just don't scale, they're not designed to. So the whole reason for using Spark is to gain the scalability. It has nice libraries, this is a nice, clean, clever way to do this, but it's also scalable. So what you're taking away from this workshop is not just a knowledge of a nice clustering library, you're walking away with the ability to write code that will run on an Amazon cloud instance at 1,000 times faster than your best workstation that your department owns. So that's the, Steve?
What does the x-axis and y-axis represent?
On which,
I guess the last clustering slide, maybe?
On this,
yeah.
It's just the coordinates. These points are all X and Y coordinates. So this is just a map. Every point's an X and Y point. And so these are just their locations in space, in X and Y space. If we go back and look at the text file for our 5,000 points, there are a bunch of X and Y values that range from 0 to 1,000,000. So that's all these are. This is our coordinate system right here. And our cost is just the distance from each point to its cluster in that coordinate system. Let's see, I'm finally catching up with the chat thing here. Let's see, can you save and retrieve models? Yes, you can save models. Models usually have a save method in most libraries and languages because sometimes it's expensive. All the knowledge that you trained them for took you 2 hours to run and train. So it's nice to be able to save that. So yes, most models have a save method attached to them that allow you to save them. Cover using a script rather than an interactive shell bit later. Oh, Brian covered that one. Yeah, you can, all these things can turn into a script, only you need to stick that little bit of header on it that I mentioned way back on the first 5 or 6 slides there, and then they work as batch jobs too, because very often you do these things exploratory and experimentally, and then you do want to run them overnight, or run them every night, or run 10,000 different ones because you're doing a parameter space search. So these things are all very script batch fileable, turn into nice batch file scripts. Okay, I think that I've caught up on most of the questions there. I need to figure out why this chat window quit scrolling itself, but I'll pay attention to that from now on. Let's see. Give me 10 seconds here to scan these. Variation. Okay, some questions about editing here in the shell. Okay, it's a reasonably decent shell with IPython, but again, if you're going to do tons and tons of this stuff, you probably want to work in a nicer IDE eventually. Let's see, okay, and I guess we're caught up. Specify the optimal cluster radius as a parameter. No, you can't do that here. I mean, that's orthogonal to what Kmeans is trying to do. It's trying to figure out its own clusters. You can specify a metric. So it's a slightly more sophisticated question. So don't worry about this, most of you. But if you want to specify a metric, an alternative metric, you can squeeze that in there. But you can't. That's the way Kmeans works. Is it's just trying to optimize your metric. So you can't pick a cluster radius. NetCDF, HDFS, HDF5. I am almost certain that the first one has a Spark plugin, and I am certain the second one does. So there are Spark plugins for those, yes, which are wonderful for those of you that are working in scientific data sets. Those are common file formats. The Spark wavelet scattering transform routine. I don't know. Off the top of my head, I wouldn't be surprised if it did. I wouldn't be surprised if it didn't. That's a borderline kind of popularity thing. Okay, let us move on, and we'll come back to the next group of questions before they build up too much. Okay, one of the things, a very important thing that we've been investigating here is our intro to the topic of dimensionality reduction. And this is going to be something that we come back to again and again over the next day and a half, and something that if you get involved in machine learning will dominate your analyses of data. And this is the idea that we're going to be working with the data that's usually in much higher dimensions than our two-dimensional data set that we have here. And I'll explain to you why that. You might, if you're new to this, you might not understand why is data always going to be in these higher dimensions, or what, isn't that an odd case that we have higher dimensions? No, it is the typical case that you are working in dozens or hundreds, is not the least bit uncommon, of dimensions. So that is just the common way of working with data in machine learning. Is you have very high dimensional data. Again, we'll come back to this and see why that is, but take that as granted right now. Working in high dimensions has great difficulties with it because it's hard to visualize, but it also has some mathematical characteristics we'll look at that make it subtly difficult to tease meaning out of it. So reducing the dimensionality of data, somehow taking data that's high dimensions and reducing its dimensionality down, can be incredibly, incredibly important, and very often is exactly what your machine learning algorithms are doing. Whether it's something like we're about to look at principal component analysis, or whether it's something like tomorrow with deep learning and neural nets. Most of the time, what you're doing is you're somehow reducing the dimensionality of the data down, because that gives us some insight, that gives us some learning, some ability to predict things better. So this whole dimensionality reduction thing is something that we're going to find underlies so much of machine learning, and that applies across every application area and domain. So these last two here represent a principle that will also become clear, which is that learning is often a way of finding a way to compress our data down. And we've already done that in a small way with clustering. Clustering is basically saying we have 5,000 data points, and we can either store all 5,000 of them in a list like we did, like we started with, or we could instead say that each one of those data points we found out really belongs to one of 15 clusters. So let's say that those data points that we were just looking at were, okay, let's pick something that's really topical at the moment. Let's say we're disease outbreaks. And we found out that those clusters happen to center on, say, nursing homes or schools, right? That might be the kind of analysis, epidemiological analysis, that's really important right now. So we found out we had disease outbreaks centering around those schools. Well, now after you've done that, you've really taken those 5,000 people and instead you reduce them all down to each one of them. Instead of having a coordinate in space, you can say this one belongs to this nursing center, this one belongs to this daycare center, this one belongs to this school. Now each person, instead of having a coordinate, their address or whatever to define them, instead just has a very simple label, the location that they're at, the facility that they're associated with. So we reduced 5,000 points in 2 dimensions down to 5,000 points that can be labeled with one of 15 locations. So we took 2-dimensional data for each person and reduced it down to one of 15 labels. That's a dimensionality reduction. And you might say, why would I do that? Well, what you've done is you've just learned where the outbreak centers are. You've just found centers that represent where the hotspots are. So that learning and reducing data down and compressing data are often very much the same thing. And we're going to find out that that principle applies to very, very different looking problems that we approach with very different looking methods and very different looking software. So that's pretty universal. So that is where I'm introducing this tag here. And this is our dimensionality reduction tag here, is this impossible triangle. So whenever we see this pop up again, take note, we are coming right back to a technique that in the end is reducing the dimensionality of our data set. And clustering is our first step into this world of dimensionality reduction. But as I said, it introduces the question of, do we really have all these dimensions? Is, why are, you think your problems, I don't have a lot of dimensions in my problem. I'm a chemistry person, I'm working with molecules, whatever. Dimensions pop up constantly. So let me, again, give you some practical examples here. So here's one, which is customers for, say, Amazon. And if you're an Amazon customer and you buy stuff off of them, and they keep a list of everything that you bought across all their categories, and they got millions of products. Let me see what my next slide is, so I know when to go on to it. Oh, that's just a pop-up. So we got millions of products that Amazon has, and these are the things you buy from them. And they might keep track of it, though, by categories. So Amazon might say that you purchased $800 in children's clothing. You didn't buy any pet supplies. You paid $450 for cameras, dash cams, or security cameras or whatever. You paid $350 for storage containers. So didn't buy any romance books. So these are the categories that they track for you. So they see what categories you lump into. And maybe if you go to Amazon, you know how they have everything in categories, right? When you're on a product, if you look up above, you can see this hierarchical list of what categories you're in. And there's subcategories. It's hierarchical. You could be in tools, and then you could be in power tools, and then you could be in drills, right? So they got all these categories. And let's say, for the sake of argument here, they have 2,900 categories that they sort you into as a customer. So they've got to keep track of 2,900 things for each customer, because this is a good way to characterize you as a customer. Do you have a pet? If you don't have a pet, I don't really want to advertise or suggest dog food to you, right? So, or pet products in general. So these categories are a good way to characterize you as a customer. Only 2,900 categories is a lot of categories, and that might be what they naturally keep. So instead, and so this is, by the way, the dimensionality of this is 2,900. If we got 2,900 categories, then you as a customer are a 2,900 dimensional vector. And the reason we can say you're a vector is each one of these is kind of, I'll introduce for those of you that are comfortable with it. It's obvious that each one of these is kind of a basis in that vector space. For those of you that aren't real comfortable with linear algebra, haven't done a lot of it recently, a vector has a couple of components to it. If we've got 2 dimensions, you can think a vector in 2 dimensions tells us where you are in that space. Our data points that we just looked at in our clustering problem were in 2-dimensional space. We could draw a vector to each one of those points. That tells us where it is. Well, if we got 2,900 things with each with a magnitude, that's a 2,900 dimensional vector. So I hope that if you're not used to thinking in high dimensional spaces and with vectors and everything, you realize, it's not that big of a leap. It's just saying, how many different numbers do I need to characterize me as a person or as a customer? And it's a 2,900 dimensional vector. So it's very, I'll come back to these questions here when we get down to talk about vectors. So we have 2,900 dimensions. Okay, if we take our newfound clustering expertise, we can actually apply clustering, K-means clustering, to all of our customers, our whole data set of all of our customers. Each customer has, with each one of them, 2,900 points. And we have 1 million customers. So we have now 29 million points scattered around, excuse me, we have 1 million customers. We have 1 million points scattered around, I just confused myself here. We have 1 million customers scattered around 2,900 dimensional space. Okay, so that's what you basically have when you have a list of 1 million customers, each one with 2,900 categories that they might have entries into. A lot of those categories are going to be zero. For most customers, you might imagine most of them are zero. That would be pretty sparse, and that's typical of a data set, is for it to be sparse. A lot of zeros for every average person. Each customer might only have 50 or 60 entries out of those 2,900, but there's 2,900 potential entries. And each person, again, only has 40 or 50 or 60. So we can imagine that we could somehow, if we could crush this data down, we might learn something about our customers. If we do a dimensionality reduction, we go from 2,900 dimensions down to something smaller. So if we take our clustering algorithm and apply it to this data set, and Kmeans is perfectly happy for you to point it at an RDD where each element has 2,900 dimensions to it. It's not intimidated by 2,900 dimensions at all. Just like it's 2 dimensions, we cluster into nice visible 2-dimensional clusters. In 3 dimensions, you might picture assembling a bunch of kind of spheres and things in space. In 2,900 dimensions, it'll figure out what points cluster together. So it's a much more challenging problem, but clustering, that's what it does. So 2,900 dimensions, we cluster things. And we find out that we have 80 clusters. And that shouldn't surprise us, because we would expect that people that buy some types of items buy other types of items. People that buy children's toys probably buy children's books. That wouldn't surprise us a whole lot, right? And they buy strollers, right? So clustering is a natural thing. We expect it. But we find that we have 80 clusters, and we do this with our normal K-means clustering, right? We see our error go down and down and down, and we go, oh, it looks like 80 is a pretty low number for our error. So we have 80 clusters defines our customers. Now we can go back to our customers. And instead of saying every customer needs 2,900 entries to represent them, instead, we can say how tightly each customer is represented by each cluster. So you, as a young parent, might be really close to that young parent's cluster of things that in our 2,900 dimensional space represent strollers and kids' toys and children's books. And I can tell you're really close to that. You are probably a young parent, but you might be very far away from the cluster of, say, knitting, people that are knitters. So these are our 80 clusters that we found. They start to summarize people into categories. These are not Amazon categories. Amazon just has product categories. These are instead categories of people and enthusiasms and buying common interests. And so we can characterize you by how close and far you are from each one of these clusters. Now, these are completely contrived. And in reality, these clusters aren't going to be so clean and easy to distinguish, but they're definitely going to be clusters. And now we have a way, instead of representing you in 2,900 dimensions, we can represent you in 80 dimensions. So I hope you're following along with me, because if the intuitive side of this makes sense to you, that, oh yes, I can see how products cluster together and people would naturally gravitate towards certain clusters on average, and you can be represented by how close and far you are from different clusters. If that intuitively makes sense with you, then what you're really doing is playing along with the same thing, which is that we've got 2,900 dimensional vectors. And by clustering, we can reduce everybody to an 80 dimensional vector. It's the exact same thing. It's the same thought process. So even if you're not comfortable with linear algebra and high dimensional spaces, that's fine. Are you comfortable with the notion that we're basically representing people by their general characteristics instead of having to go through and label them by every minute detail? And if you're comfortable with that, you realize, okay, we've done this dimensionality reduction, and at the same time, we haven't just saved ourselves a few bytes in memory for each customer. We didn't just do this because now we only have 80 values for a customer instead of 2,900. That wasn't our motivation. So it might be, I mean, maybe you're really short on space or something, but that's not generally machine learning's motivation in the age of big memory and massive data sets. Our motivation was that now that we've compressed every customer down to these 80 values, or 80 dimensional space, we can target them much, much better with their interests. We can see that, that this person is a young parent. We should definitely target them with things that are interesting to young parents. And they are definitely, we don't want to send them any coupons for knitting stuff. And there are other things that are totally different than this, that might be relevant to them. I mean, they absolutely, for whatever reason, buy plumbing supplies. Maybe they're remodeling a home or something. So you can see that. You could also learn things that you might not have known before about the way things cluster together with your products. Like, for example, people spending on child toys and children's clothing and children's books, that's pretty obvious, might also cluster with cameras, people that spend on cameras. Maybe that was obvious to you, maybe it's not, but maybe you realize afterwards, oh, These people are buying dash cams for their car because they're more safety conscious. They're buying baby monitors and security cameras. So to me, it might not have been obvious that people that, that are young parents spend money on our camera category. But this machine learning algorithm figured it out for us and figured out how to target customers better. Again, for promotional cases in our crass Amazon example here. But in general, this learning process of compressing things down allows us to discover relationships that we didn't know otherwise. In the case of right now epidemiological models, you hope that you can figure out things about which kind of groups are more susceptible than others. The genomics people are furiously working away trying to figure out which genes might correspond to high risk factors or low risk factors for COVID. These are all clustering type problems. You're trying to figure out how things cluster together. Okay, so I hope that that makes sense because we're going to come back to it again and again, this dimensionality reduction idea as we go along here. As a matter of fact, this is a good time for me to point out to you that high dimensional spaces are computationally very difficult to deal with too. So it's a reason why, again, besides saving space or maybe learning something, it's not good to have super high dimensions if you can avoid it, because there's some things that happen in high dimensions called generally lumped together as the curse of dimensionality. So it's a little bit fuzzy of a term. People lump together a lot of effects about high dimensional data and why it's hard to handle under curse of dimensionality. But the general notion is important to understand. And that is that when we go into higher dimensions, some non-intuitive things start to happen that make it difficult to analyze data. Maybe one obvious thing, the one at least I'll graph here, I'll mention a few others. One obvious thing is that all distances in high dimensions start to look about the same. Everything looks like it's the same distance from everything else. What does that mean? That sounds absurd and it doesn't seem to make sense, but let's look at how this actually happens. It's just an inevitable result of Pythagorean's theorem. It comes right out of something that you learned in middle school. In 2 dimensions, let's say we have a piece of paper on the floor that's 1 meter by 1 meter, and we just randomly throw darts up in the air and they come down on the paper. In 2 dimensions, the distance between any 2 of those random points is going to be about ½ a meter on average. So we got our piece of paper on the floor. Like I said, we throw 2 random marbles down or whatever, and you just measure the distance. Some of them will be real close together. Some of them will be, far apart. But in general, most of them are going to be about ½ meter apart. In 3 dimensions, so now let's say we got a fish tank, and it's 1 meter by 1 meter by 1 meter, and we got 2 goldfish floating around in it. And anytime we walk up to the tank, how far apart are those goldfish going to be, assuming that they're random goldfish that have no particular affinity for each other? On average, they're going to be about 0.7 meters apart in that fish tank. Sometimes they'll be close together, sometimes they'll be further apart, but on average, this is about how far apart they will be in 2 dimensions. Well, okay, we can start to see a little bit of a trend here happening, but basically, if we take just Pythagorean theorem, x squared plus y squared, and we keep extending out x squared plus y squared plus z squared plus a squared, we keep going to higher and higher dimensions, we're going to find out that in our 10-dimensional fish tank, right, if we're working with 10-dimensional vectors, that our fish now in their 10-dimensional world are going to be about 12 meters apart in our 10-dimensional 1 by 1 meter on a side fish tank. Okay, that's the geometry of higher dimensions. But more importantly, you can see this is getting a little bit more peaked. And as a matter of fact, if we keep extending this out, at 100 dimensions, our fish are going to be about, did I say 12 meters apart? I said 1.2 meters apart. In 12 dimensions, our fish are going to be about 4 meters apart. But this is really getting quite peaked. In 1,000 dimensions, our fish here are going to be about 12 meters apart, but they're almost all the same distance from each other. The ones that you think would be close to each other and far from each other are still all about, 12.5 meters apart. And this is just Pythagorean's theorem if you keep extending it to higher dimensions. So this is not that complicated. This is not some, really bizarre differential geometry kind of argument or something. This is just working in higher and higher dimensions with Pythagorean's theorem. We find that everything starts to be about the same distance from everything. And it's a bizarre concept to extend from our 2-dimensional and 3-dimensional world, but it's absolutely true. This means clustering algorithms, for example, really have their work cut out for them because they're all about figuring out how close points are to each other. Can you imagine how hard it is to cluster things when all the points are about the same distance from each other? It's a lot harder to form clusters, right? So this is one of the things that happens in higher dimensions. Now, related to this are a host of other effects. For example, vectors, random vectors, if we have 2-dimensional piece of paper on the floor and we take 2 needles or nails and throw them down and we say, how do they orient to each other? On average, they're going to be like 45 degrees on average from each other. Well, as we go to higher and higher dimensions, they start to all look like they're perpendicular to each other. again, it's not intuitive, but it's very straightforward to derive from simple geometry as you just extend things to higher dimensions. A sphere takes almost no volume up inside of the square, the unit square, and that means it's very hard to sample. So these are all kinds of problems that show up in higher dimensions that just don't make sense to us in our lower dimensional world. We don't think well in high dimensions. But this cursive dimensionality is something to be aware of when people start casually talking about clustering in hundreds of dimensions, because your results can be a lot less stable than you think. And this is where checking out different random seeds and whatnot becomes much more important. So high dimensionality, the cursive dimensionality is a term you'll absolutely see used in any reasonably deep exploration. Any beginner level book of machine learning will get to, within a couple of chapters, some version of the cursive dimensionality, because it shows up as soon as we get into higher dimensional vectors, and higher dimensional vectors, I hope you're starting to believe, are quite common in machine learning. Related to this is the fact that the distance that we use is not always some simple Euclidean normal kind of geometrical distance that you're used to. It is so far in all of our examples that we did, but you can imagine many simple cases where it's not. For example, if you're solving chess problems on a chessboard, the distance on a chessboard is not a Euclidean distance. Instead, we got to move like this, right? Which means that all of a sudden this red line and this blue line have the same distance on a chessboard because of the same number of squares. This is common enough. It's called usually the Manhattan distance, because it's like the blocks in Manhattan, or a taxi cab metric. So we can see that the distances that you use can be varying on some problems versus others. And you might say, okay, well, chess is not at all what I'm interested in. Well, how about something as basic as natural language processing, like we've been talking about so far? If you care about the distance between words, for example, the way that they're spelled, let's say you're just writing a spell checker, and you think somebody typed in a word, and you think, it's not a word in your dictionary, so you're trying to suggest a word to them. How do you figure out what the nearest word is? If you start looking at the way you compare strings, misplaced strings, or how far away am I in terms of a keyboard distance to mistype a key, or maybe I care more about the phonetic distance because they guessed that an A was an E instead. So there's lots of different distances that you might use in just trying to do word correction. And so you can care about things in different ways. And so the metric for distance that you use very much depends on your problem. It's not always just some simple Euclidean distance. Sometimes it doesn't even actually qualify as a metric because you don't even have the triangle inequality it doesn't show up a lot, even if you start digging into the details of this. But at any rate, these are details that show up quite often. They're not esoteric things. So let me talk about, this thing is not scrolling again. This is maddening. Okay, no, there actually aren't any questions. Okay, amazing. Let me talk about one very, very, very powerful and widely used technique that you now have available to you with the kind of tools that we're using, which is principal component analysis. So if you get into any of these more sophisticated machine learning algorithms, they'll often compare themselves or involve themselves in some way with trying to figure out a way to reduce dimensions, and principal component analysis is often a go-to, or at least a benchmark, to figure out how to do that. So what does it mean? I can explain very quickly what it means in an intuitive way, so you don't have to be intimidated when you start seeing it show up in references to all the other things that we're going to cover. If we've got a 3D data set like this one right here, so this is a data set in X, Y, and Z, and it's going through space. This is the shadow down below that it's casting. So it's going through space like this. So it's some data points clustered along this axis in space right here. And if you look at this data, you might get the idea that there's kind of a trend to it, right? It seems to be clustered along this line right here. So as a matter of fact, it definitely looks like, it's clustered along this line. It definitely looks like this is actually, in some sense, almost one-dimensional data. How do I mean that? I mean that if you can tell me in one dimension where it is along this line, I can give you a pretty good guess as to where it is in all of space. Right? So even though each point here has 3 coordinates of X, Y, and Z associated with it, in some sense, we can really represent this thing mostly by 1 coordinate. We can reduce its dimensionality by a factor of 2. So this data really is mostly, now it's not exactly going to be right, right? If I tell you, if this point right here, if I say it's along this line, it doesn't tell you exactly where it is, but it's mostly there. As a matter of fact, we can start to quantify how much this effect is true. How effective is this component, this first principal component, in telling us where this is located? And so, as a matter of fact, let me see if, yes, let me go back to this one. As a matter of fact, what I've actually drawn here, using principal component analysis, is how I found this axis. And what I've actually drawn here is all three components of this data set to tell us how closely they are related in space. The other two components are so small here, you really can't make them out. I think there's a couple of red pixels here if you were to zoom in on this, because the components in the X and Y direction are very small compared to this component. Well, I should say in the other directions are very small compared to the component along this main principal component. So principal component analysis, we set it loose on this data set, and we'll see how to do it. I'll show you some examples of it. We set it loose on this data set, and it comes back and says the first component is very large, has a very big significance, and predicts very well where the data points are. So your one dimension describes your data pretty well. And then it also can come back and tell us, by the way, there still is some other variability, and I'll give you those components, but in this picture, they're so small you can barely see them. Let's look at where they're a little bit bigger. So here's a flatter data set, and it's a little bit, I hope you can kind of tell from the shadow down below, this is kind of data set that's scattered kind of in a plane here. So this data set is kind of viewed on edge. So here's my view down the edge. If we look at this data set from the edge, we just rotate this box around, you can see the data is mostly flat. It's mostly in a plane here, which means this data now, again, it starts out as three-dimensional data. Each point really has three dimensions, but it's pretty well characterized by its first component, gives us its direction pretty well, but not as well as it did before. Now there's also a pretty strong second component. The second component kind of gives us its direction in the plane, in space. So if you give me two components for this data set, I can give you a pretty good guess. You tell me where it is along this line, and then tell me where it is in this plane, in this perpendicular direction. I can give you a pretty good guess on where that point is in space with two dimensions, not needing all three. So this is principal component analysis on a data set that has two pretty strong principal components. We can reduce it to two dimensions. So you're seeing right here our ability to take data sets and reduce their dimensionality down. Principal component analysis is a very, very common technique. It's got some limitations in it. It's linear, but I'll show you what that means in a second here. But because it's so well understood, it's such a direct algorithm to apply, it's very often the first go-to to see if you can somehow reduce the dimensionality of the data set. Okay, let's look at this in a more realistic example here. So let's say we're trying to do a Zillow type of analysis to predict home values. And this is an actual real problem. I'll give you the data set for tomorrow after we learn neural nets, which are a powerful enough technique to do this pretty accurately. I'll give you a data set for Boston, and you can see how well you can predict home values for Boston. But let's say that we're starting this problem from scratch here, and we got some home data here. So we have the coordinates of the house. We have its last sale price and when that was. We have the width and the depth from the floors of the house, number of beds. So we got some information about the house that we think can be useful for predicting its home value. And you might guess that some very important factors are the neighborhood, which probably correspond closely to the coordinates. Is it close to good schools? Is it next to the city dump? So, I mean, you can guess this will have some clustering in some sense that goes on about it. As a matter of fact, we might apply clustering just to these two coordinates and see if we get some clustering. We have last sale price, and you can imagine that correlates in some way that we could do with regression. But here we have something that we think immediately are some dimensions, because these are all dimensions that represent this house, right? So these are all, like I said, this is, let me see what my pop-ups are here. So like I said, the latitude and longitude might give you some pretty obvious one, but right here is another couple dimensions that we might be able to reduce down because we got the width and the depth of the house. And any of you who pay any attention whatsoever to home values know that houses are generally characterized by their square footage. You say a house has 1,200 square feet or 3,000 square feet. You don't say what the width and the depth is generally. And that gives you a clue that probably this dimensionality can be reduced, that these two numbers right here can be reduced down because we don't really care about the footprint of the house. We just care about the square footage. And again, it's not always going to be true. Maybe there's a trend where people like frontage, and they used to call it frontage in houses, a wide home because it looks more impressive from the curb. So maybe this isn't 100% true, but maybe there's a strong tendency, a strong first principle component to this. So let's take a look and see what happens if we apply PCA to the house price versus the width and the depth. And if we do that here, we will see that here's our first principle component. Here's our house prices as they correspond to width and depth. They definitely go up as our width and our depth grow larger as we go further out here, they go up. I wish I put some shadows here because it would be down here. They definitely go up, but they don't match this line very well. And why is that? Well, that is because PCA is good at working with linear values. And in our case here, width times depth, I don't know, I'm heightened here. Width times depth is not linear. It's not a linear relationship between the values. If it was plus of the two or something, it would work, but it's not. It happens to be a quadratic relationship. We're multiplying things instead of them being linear. And so this is a big distinction in machine learning between linear techniques and nonlinear techniques. Linear techniques can't deal with anything when things start to get multiplied together, even something as simple as this. So principal component analysis here, as good as it is in general, as a first approach at least, fails miserably here. Well, it doesn't fail miserably. I mean, it gets kind of the trend, but it doesn't match very well. Where as soon as we compare this against square footage, if we do the width times the depth ourselves, we can see it matches pretty well the data. So it is good at capturing linear relationships, but it's not so good as soon as things aren't linear. So it's got limitations. So these are the kind of things that you need to be aware of. And tomorrow we'll look at, can we do nonlinear PCA? Or can we do because there are nonlinear approaches to do this, or can we do a different approach altogether? So we will get into this tomorrow. Okay, so enough about that dimensionality reduction topic. I want to introduce it this afternoon while we have some time, and we have some time to think about it, come up with questions, and I can answer them, because tomorrow we're going to find out it starts popping up everywhere. Pops up like weeds whenever we start dealing with real machine learning problems. Tomorrow we're going to do, when I say real, we're going to do some real problems. We're going to do the Netflix movie analysis problem, recommender system problem that was worth $1 million 9 years ago. We're going to do something that was a very real problem, and they still, of course, care very much today about their recommender system, but this is the exact problem that they use for their prize competition. So it's, when I say a real problem, it's a real problem. And then we're going to go into machine vision and start recognizing real pictures and be able to talk about those classes of problems. So we're going to jump into some real problems, but again, this dimensionality reduction is going to keep popping up. So I hope you're getting a notion of why it's important here. Okay, a few words about some. So we'll set aside that greatly abstract and important overview topic, and we'll dive back down into a few Spark details before we call it a day and set you loose on exercises. And that's a few words about data frames, which data frames are basically ways of, instead of just having all of our elements in an RDD be basically these unstructured elements, at most so far we've seen that they could have a key value relationship. It's nice to actually be able to start to impose some more of these table-based relationships on things. As I said, for a while, the NoSQL thing meant just key value stores, throw out all structure to our data. Turns out that key value stores are, that having some structure in our data like SQL tables is quite natural fit for our data. It's quite intuitive and makes it easier to read and understand the code as a human. Turns out it's also very good from a performance perspective, because if we can tell the Spark system what the data types are that it's dealing with in a consistent fashion, it can do a lot better optimization than if it has to pretend that every element is a totally different type of data. And so we can do that here. And data frames are how we do that. And they're very straightforward to use. As a matter of fact, as you look through the documentation, I hope that as you've done the exercises, or as you do the exercises, you have that Spark browser page next to you. As you start to poke around, and particularly in MLlib with clustering and whatnot, you'll notice that it says these are the data frame versions of these routines. So it'll have the regular RDD versions, then it'll have the data frames. And so if you think that the data frames are a lot different than RDDs, that's not the case at all. They're just basically an RDD that has some structure that you're guaranteeing is imposed on it. Let's take a look at that. It's very straightforward to use. So the data frames type, we haven't jumped on it so far because it's not necessary for the problems we've done so far. It might not be necessary for a lot of problems you do, but it's very straightforward when you do decide that you want to use it. So it's very simple. All we need to do is make sure that every element in our RDD is the same type of structure, which is exactly what you'd expect if you want to treat something like it's a table or like it's got these fields. So if every element in our RDD looks the same in the sense that we've got a string and another string, and then a digit, string and a string and a string and a digit. As a matter of fact, the data type, the data that we're keeping in each one of these strings represents something consistently different. So first name, address, state, zip code. First name, address, state, zip code, right? If every one of these is the same, which is what we'd expect for an awful lot of data that we're going to be handling, then this is automatically a row RDD. So if we have a row RDD, we can turn it into a data frame simply by just saying create data frame and giving it the row RDD. And then we can tell it the names of the fields if we want. If we don't tell it that, it'll come up, it'll just make some generic names up. But if we tell it that, now we've got some nice names in our fields that we can handle from now on and treat this like it's a table. So there is a way to treat our RDDs like a nice table structure. And again, it's good not only for you as a human to organize things, it also helps the efficiency of Spark, because now it knows what kind of data chunks it's got to deal with. So this data frames API is part of the newer Spark libraries, and a lot of the machine learning libraries that say, hey, if you can give me a data frame, I'd appreciate it. It's better. And there are versions of it that only take data frames. But whenever you see something pop up and says it wants a data frame, don't think, oh, I don't know how this works. Just realize, okay, it's just saying you better have consistent structure on your elements and be able to tell me what they are. And that's not, again, an unreasonable expectation at all. So you can create data frames very easily. If you don't give it names, it'll just come up with these generic field names. You can create them inline as well. Like we have our parallel command that creates things inline. We can just create a data frame right here from scratch without reading it in as an RDD. So they're very straightforward. If you're a Java person in particular, you'll notice that there's a variation on that's called data sets. They're very similar, except if you've got a language with strong typing, like Java and Scala actually have strong typing, then it'll help using data sets instead of data frames. It's almost the same thing, only it can help detect errors a little bit easier because it's got strong typing. This is not relevant for Python or R, so don't worry about it, but it's very much the same idea, just taken a one step further. Okay, so we've mentioned pandas and SciPy, and that I've mentioned in passing. Once again, I want to point out that as you go back and do the exercises, and you may say, hey, I know how to do this with pandas to do the data frames kind of stuff and juggle data as tables. I know how to use SciPy to bring in clustering algorithms or scikit-learn or whatever. And again, the idea is not that this is a better library than they are. The idea is that everything in this library is scalable. Everything you do here will automatically for you run at larger scale when you put it on a cloud instance, or you put it on a supercomputer, or you just buy a big workstation with a lot of cores. It'll automatically be able to use all of those cores, or maybe GPUs, depending on which algorithms and whatnot. The point being that Spark is big data. It's scalable. It's not just a collection of nice scientific and machine learning algorithms and routines. I mean, it is that, and that is wonderful, but it is, and a lot of data connectors and plugins and that kind of stuff that you're not going to get elsewhere. But its most important thing is that everything that's in an RDD is scalable and could be many terabytes or larger in size. Every transformer you use on an RDD will recruit all of the CPU capacity in that cluster. That cluster could be a machine like Bridges, or it could be a very huge chunk of some cloud resource somewhere. So it could be many thousands of cores and many terabytes of memory. Every algorithm that you run, clustering or whatever, can use those thousands of cores. So that's the important takeaway here. So don't just think, oh, we learned some neat libraries today. You learned everything you learned today. Everything you learned today is scalable. Okay, as you do these examples here, there are a couple different ways you can run them. You can run them, you've already been in your Spark shell today, and you can just cut and paste things. You could also, there's a command that's useful in Python 3 that allows you to just run a file right off of disk. So if you want to just run the file, so if you look in, say, the clustering folder that you've got in your big data directory, you can go in there, you'll see clustering.py. It's the code that we've been looking at today. If you want to run it within the shell, you can type this. If you type this, it'll actually just read in and run that code directly. And so you don't even have to cut and paste it, that option. Okay, and I think with that, we are on our last slide, and I'll give you a little bit of orientation about how this stuff fits together with what we're going to talk about tomorrow, which is a very different approach. Well, tomorrow morning, we're going to start out using Spark, but we're going to build a very sophisticated real application, the recommender system, and then we're going to move into deep learning in the afternoon. And so here's how these pieces start to fit together, because you're learning some of the significant pieces. The whole field of AI is very nebulous. Hence, I've drawn it as a nebulous cloud here, because AI is a fuzzy term that has some people try to pin it down. There are definitions of strong AI and weak AI, and computer scientists will claim they have a good, strong definition of it. But people dispute, for practical purposes, what AI is furiously, and will continue to do so in spite of any pedantic definitions, because as soon as people are able to do a task on a computer and it's well done, somebody says, that's just a trivial algorithm. It's not real intelligence. Good example of that is character recognition, which is something we're going to start with tomorrow with our TensorFlow. We're going to start with some basic character recognition. We'll get fancier from there. But basic character recognition back in the early 90s was certainly considered artificial intelligence because it was difficult to do, recognize arbitrary fuzzy characters and whatnot. And as soon as we got good at it, people said, yeah, that's just some pattern matching algorithm. It's not really AI, it's just fancy statistics, modeling and that blah, blah, blah. Okay, but CAPTCHAs, right? Those things that are supposed to defeat you from text recognition, defeat robots at least, where they distort the text, those are surely AI because by definition, they're designed to defeat machines. So if you can learn to recognize some smeared out, stretched version of a word, that's real intelligence. That's just that, because those are infinitely variable, and the whole point is to defeat artificial intelligence. Well, deep learning neural net techniques we'll look at tomorrow make quick work of those. So then people said, oh, well, you know what? In reality, that's just a fancier version of character recognition. So that's not really AI. But, games that require a lot of intelligence, that might be AI, like chess. Chess back in the 90s was certainly, early 90s, was certainly considered to be AI because you can't solve it with brute force if you want to beat a grandmaster. You can write simple chess programs, but to beat a grandmaster at chess requires real intelligence. You're never going to be able to just solve the game tree because it's too big. You can't just solve the game tree with brute force. And so chess is real AI. And then, of course, Deep Blue came along and blew away chess, and people said, you know what, that's just fancy game algorithms, blah, blah, blah. That's not AI. Now, what would be AI would be if you could win Go, because Go has such an enormous game space that there's just no brute forcing it at all. Deep Blue is this brute force machine that could look ahead enough moves, et cetera. But Go, you can't do that. You can't memorize books, strategies in advance and everything. So Go is real AI. And indeed, Go held up as a very difficult problem to solve until AlphaGo or AlphaGo Zero, which I confuse them a little bit. I actually have them on a slide later on, so many variations of the name, but AlphaGo Zero or Alpha Zero, whatever it was, that beat the best Go players a couple of years ago, and is now beating any human soundly, is now all of a sudden gone from AI to the category of, well, you know what, that's just fancy machine learning. And so AI has this long history of being difficult to pin down. However, machine learning has been this core for a long time of AI. The traditional classical machine learning was based upon the application of the kind of things that we've started to get into, like clustering and principal component analysis, and really clever directed use of those kind of techniques, as well as some other ones, support vector machines and a handful of other things that you'll, by the way, find in the Spark ML libraries. Those kind of collection of classical techniques, which have been developed in a nice evolutionary way since the 50s in some sense, were considered to be the heart of AI, and that was classical machine learning. And they were achieving successes, but they were achieving them incrementally. It was taking a long time to get there, things like speech recognition and self-driving cars, and that were based upon these. And it was really painstaking progress. Over the course of decades, it was very recognizable progress, but it wasn't revolutionary, and it was still considered to be a long ways off before we'd have self-driving cars or text to one language to another, real-time text translation. That was machine learning. Something really amazing has happened in the last 10 years, and maybe mostly in the past 5 years, which is that deep learning, or neural nets, and they're really the same term. I mean, tomorrow we'll see why they're the same term, but the same thing. So deep learning or neural nets, which used to be a tiny little niche part of machine learning, has exploded and taken over most of artificial intelligence now. It used to be, for the longest time, neural nets were like the last chapter in a book on machine learning, and they'd explain how they're really generally useful, but they'll always be the second best technique at everything. Neural nets will never pass up these well-constructed, well-understood machine learning techniques. Well, then these two things happen in the past 10 years, one of which is big data. The big data sets that were enabled by, we looked at, the disk storage exploded and people started collecting data, and just became possible and cheap to have big data sets. Big data sets were one of the two ingredients. The other ingredient we'll look at tomorrow is GPUs. the ability to do a whole lot of computing on the cheap on your desktop. Those two pieces came along and just supercharged neural nets. And neural nets now have taken over AI and displaced as the best in category most classical machine learning techniques. So deep learning is now the best at everything from machine translation to driving cars to playing chess or playing Go or predicting home values and all of these things. And we'll understand that more tomorrow. But that's how these pieces fit together. So that's how we're creeping along here. We're building our foundation up in order to jump into that tomorrow. Okay, with that, we are done here today. A little earlier than usual because the questions haven't been as easy, haven't been as interactive. Without our wide area classroom, I recognize it's harder and less dialogue going on with the questions. So we have a little bit more time here to work with. So I am happy to answer questions until we run out of questions here, and I will try to do them in real time and interactively as we come on. So let me back up here and see if there's any. No, it looks like it's been pretty quiet here.
If we go back about 45 minutes ago, somebody asked, should we do clustering first, then reduce dimensions, or vice versa?
That's an excellent question. And the generic answer, it could depend a little bit on structure data. The generic answer I'll start with is you typically reduce dimensions first and then do clustering. And that's for a couple of reasons. One of which is that the dimensionality reduction with something like PCA is usually a lot faster than clustering. So it's easier to attack the bigger data set with dimensionality reduction and then go after it with clustering when it's got less dimensions to work with. So that's typically the reason to do it. It's just more efficient. But it also, and maybe I can point it out on this slide right here, it also is hopeful for you that if you reduce stuff with reduce a data set with, say, in this case, PCA, principal component analysis. So maybe we take our three-dimensional data set, and when we reduce it here into this plane of two-dimensional data, we find out that our data is really a plane here in 2 dimensions. So let's picture we completely throw out the 2 dimensions, we just reduce it to a plane. As a matter of fact, this shadow down here isn't a bad, it's not completely accurate because there's a little bit of an angle, but this shadow down here might represent the plane of this data up here. So if we do PCA on it, reduce it to a plane, we might hope then that in this plane, there are visible clusters. Turns out there aren't a whole lot for this example right here, but you might hope that. And in some cases, that's absolutely true. As a matter of fact, tomorrow I'll show you a case with vision recognition where that's absolutely true when we look at character sets. So if you do PCA first, again, it's usually quicker, so it works better on a huge data set. You do the PCA, and then you hope that if you do clustering on your reduced data set, that the clusters are obvious and stand out. So that's typically, in a generic sense, the approach. But again, you can come up with cases and applications where that's not quite true, where you need to do the clustering first in order to, because the data is clustered in those dimensions first. So not always true, but that would be by default. If I'm flying blind, that would be my first attempt, would be PCA and then clustering.
Any kind of data can be transformed to RDD, or is it just for collection of data with some specific characteristics?
No, RDD. So by the way, Steve, I am assuming that everybody can hear your voice just as clear. I'm not repeating the questions like I usually do in our wide area classroom. So because your enunciation and your volume are so good, I'm not going to repeat the questions here. If that becomes necessary, people let me know, because it's important you understand the question before I waste your time answering something you can't understand. Geez, Steve, I just forgot the question you asked. Repeat yourself.
Any kind of data can be transformed to RDD, or is it just for collection of data with some specific characteristics?
No, RDDs are very, very generic. As a matter of fact, that's one of the reasons why using the data frames is nice, because RDDs are so generic, the system's so compliant, you can cram just about anything into it, any chunks of bytes. Picture, you can do images, and it's actually not unusual. You can do images with as elements of RDDs. So they can be image data. So any bunch of bytes can be the data. And that's why, again, the data frames can be nice, because if Spark does know what kind of data is, it can make some assumptions about allocation and everything else. But no, RDDs are very, very generic, and they can take any kind of bytes that you want to stick into an element. It is perfectly happy to wrangle that chunk of bytes. And again, a good example of that would be something like images or audio files, both of which, well, the first one of which is very common, and the second one of which I've seen juggled by Spark. So just fine.
Here's 3 questions, so you can take them one at a time or whatever. Could you share with us also Slurm SBatch script to submit Spark or Spark jobs into cluster? That's one.
Okay, let me address that. Let me take them one at a time, if you will. It's just that Spark submit command. So if we go back to, it's still actually this lecture. So if we go way, way back to where we were earlier, is it here? Yes. So here it is. It's this slide right here is everything you need to know. If you want to take anything you're doing interactively and you want to turn it into a script, the first thing to do is you need to make sure that you have this at the top of your script, because this is what will actually go and find and set things up front. So you need to have this on top of your script. And then once you've got that script, you can just submit it. You should make sure that the Spark module is loaded first, or it won't know what the Spark submit thing is. But then you can submit the script as this. So this is the complete recipe for submitting a batch.
And
which,
maybe,
by the way, I don't imagine most of you want to do that for the exercises, because this is typically more tedious. You got to wait for the output to come back, et cetera, et cetera. So this can be wonderfully useful for production runs, but I think for workshop purposes, most of you shouldn't be interested in that process. Okay, Steve, next question.
Brian pointed out regarding these questions that there's instructions in the Bridges user guide at psc.edu to do this in a yarn cluster. There are other methods. We will document some of those soon, but setting up such a cluster is beyond this talk. And the second question of the 3, and maybe example for Spark in a Python script, not interactively. Is there any command to use?
Okay, that's pretty much what I just covered. So I hope that answers that question. So if you want to do Spark not interactively, do it as per that slide right there.
Is Spark data frame designed to use parallel computing capability by default, like RDD?
Yes, absolutely. A Spark data frame is really just a little skimmed layer on top of an RDD. So yes, absolutely. Data frame, it will do everything in parallel, just like an RDD.
How are missing values handled or represented when using RDDs or Spark data frames?
I don't know what the questioner means by missing values. So if you can elaborate on that. I don't know what a missing value is in an RDD. I mean, an RDD doesn't have missing values in that. It's just a collection of things that you do have. If it's not there, it's not part of the RDD. But maybe I'm misunderstanding the question. Please come back and elaborate on that a little bit more if you'd like.
How is RDD compared to HDF5?
Okay, RDDs and HDF are two different things. HDF5 is an actual format with lots of meta information that's meant to live on a disk. So it's a file format, like the many, many other file formats that Spark can deal with. An RDD is not a file format. It's something that just lives in the Spark system, and that's the only place it lives. It only lives within the Spark system. It might be data that's on memory. It might be on disk. It might be on both. It might be spanning it. It's a bunch. It's just it's all the stuff that's dynamically living in Spark when you're running it, and it's nothing else. So it is not a particular file system or format or organization. It is its own thing. Whereas a file format like HDF5, is definitely a great, useful, portable way to store data. And it's portable. It's meant to move from one machine or session to the next, and then it can be read into an RDD. An RDD is not meant to be portable, or it doesn't have a specified format because it's not meant to be portable or moved around. It just lives inside of Spark, and that's the only time it lives.
Regarding the missing frames, like what would be represented using np.nan?
Oh, well, like not a number, an NP. Well, I mean, that's an array. And so that's an array, and having not a number in there is fine. I mean, an RDD doesn't have, I mean, I guess if you want to say, if you have integers and I do an operation on an integer that makes it not a number, will that be a not a number in Spark? And I guess I would have to say that comes down to like not a number in general, to the math model it's using. So it could be maybe not a number's allowed in a Spark element, and maybe it, is or isn't. I mean, that's a math specific portability, thing. So that's so yeah. So if you had a bunch of elements and you did like a mapping that did a divide by 0, and you wondered if that turns into not a number or an inf or something like that, that's going to be very application dependent. So that's I think I see where you're coming from now, but yeah, that's very application dependent.
Is there any library that can remove punctuation, stop words, and stemming in languages other than English?
Yes, absolutely. The language toolkit has versions of those 4 other languages, and you'll see that there as the options. If you look in the man pages of the documents, online documents, you'll absolutely see that those are intended to be portable to other languages. And that's important because a lot of natural language processing is involved with machine translation, for example. So yeah, absolutely. Those work well with other languages, many other languages.
How can we change image file like .png, excuse me. How can we change image file like .png format to RDD format?
Okay, well, it's .png is fine. A .png could be an element of an RDD. There's an RDD element. It can be any kind of bytes, and so that could be a PNG file. It can be any pile of bytes that you want. You will find that most of the connectors, the Spark connectors to read in things like graphics libraries or audio clips or whatever, do that kind of translation, if you will, for you. But if they weren't there, you can read in raw bytes if you want as RDD elements. But for things like PNGs and common graphic files, those pieces are built in there. And furthermore, you'll find that some of the graphics processing libraries have pieces built in to analyze that stuff and do it for you. So you'll find those pieces there, those image processing pieces there. Plus, you could actually run, Python. Yeah, I mean, I'm trying to think if it would be viable to run matplotlib code as a mapping. I mean, I don't want to stray in that territory. It may or may not be possible. Point is that it's easy to do that, and it's direct to do it, and you can find lots of examples. So if you do, like, say, Spark image processing, if you Google that, you'll find lots of examples along those lines. Now, you may want to hold off on that a little bit, in that if you're really doing a lot of image processing, you may be more interested in how to accommodate that with TensorFlow, because neural nets, which are fantastically effective at image processing. In which case, maybe hold off a little bit until tomorrow, and we'll look at how TensorFlow, for example, allows you to read in PNG files and manipulate those and do things.
All right, a couple questions here. I think they're related. What is the fundamental difference between regular ML and DL? I understand that DL is neural net and is kind of a subset of ML. For instance, is there a fundamental difference in how regular ML and DL approach a problem? Are there classes of problems that are better handled by DL as opposed to regular ML, and vice versa? For example, how do we decide whether to use ML or DL?
Okay, that's a very loaded, interesting question. First of all, let me make it clear that technically deep learning is a subset of machine learning. So deep learning is part of machine learning. However, because they're so separate, and because the way one's exploded and burst out on the scene, people typically will say something like classical machine learning to distinguish between the two. So I think actually my slide was not a completely incorrect Venn diagram in that sense. So in some sense, where are we here? This is actually the case, is that deep learning is a subset of machine learning. However, because deep learning is so different in its approach and is now just exploded, people will say, when they say machine learning, they might imply classical machine learning. I hope I consistently, as much as possible, say classical machine learning to distinguish between the two. So that's the real technical relationship, is deep learning is a type of machine learning in a sense. Where to apply the classical techniques versus the deep learning is a very rapidly moving border. 10 years ago, deep learning had a very small subset of tasks that it was considered to be superior on. Now, classical machine learning has a very small shrinking number of islands that it has any kind of supremacy on, and deep learning has just taken over so much of the landscape so rapidly. So the border has shifted an awful lot. Now, smart people say that you really should have a good grounding in machine learning, classical machine learning techniques, because these things I'm talking about, like dimensionality reduction and clustering and whatnot, absolutely apply to deep learning. And I hope I emphasize that a lot tomorrow in the deep learning talk. So you don't want to forsake machine learning, classical machine learning, but more and more neural nets are displacing the successes in machine learning, or they're superseding them in a sense. They're performing much better than the classical machine learning techniques. So things like that were, boosted trees and random forests and whatnot that support vector machines that for a while, held their ground in certain areas are now being rapidly displaced by different neural net architectures. And the deep learning architectures continue to proliferate. That's something we'll talk about a lot tomorrow. And so, where you draw the border between, where you should expect to be successful in classical machine learning versus where you should just throw up your hands and say, let's just jump in with deep learning and neural nets. The border has shifted so fast, incredibly rapidly. I mean, in the space of 5 years, it's shifted. And you can see this quantitatively because machine learning, and something I'll emphasize tomorrow, uses an awful lot of competitive type approaches to data sets. It's a wonderful thing in that there are these benchmarks, which you're given a data set and you're given an objective with a data set that's quantifiable, and then you just have competitions and people compete against each other. I'll emphasize that a lot tomorrow because they're wonderfully good ways to stoke progress. With Kaggle competitions, win yourself some money. Because these standardized competitions make it so clear which techniques have supremacy, you can see where deep learning has just one after another checked off the machine learning as the best way to do these different problems. And so it's taken over on reinforcement learning and unsupervised learning things where it didn't seem like it would be as applicable. So we'll dive into that a lot more tomorrow, but your question is extremely relevant and important and widely discussed and widely debated amongst people that do this kind of stuff all the time. And maybe after tomorrow, when we cover deep learning, you'll be able to more appreciate articles and research papers and that to discuss exactly that. When you pick up an article, one of my objectives is when you pick up an article and it discusses the great success of this neural net at attacking this problem, and somebody compares it to a classical machine learning technique, is that after tomorrow, you'll be able to understand an awful lot of that discussion. And then you'll be able to follow along with what I said is a active and interesting, I won't say controversy, but discussion, certainly. Sorry for the long-winded answer, but it's an interesting question, and people will get on their soapboxes who work in different areas of machine learning to champion their approach or their cause or their vision for the future.
How is the physical structure of RDD, array-like or dictionary-like?
It is. So first of all, you're probably not supposed to ask that question. It's supposed to be magic. Don't look behind the curtain. In reality, because it's mostly driven by a hash table and it's to find and access the things, in some sense it's dictionary-like. So in reality, it's implemented as the most efficient hash table type of operations they can come up with to manipulate the data rapidly. But they're not guaranteeing that or telling you that or exposing any of that interface to you. So as far as you're concerned, it's just an unordered set of data. But yeah, in reality, behind the scenes, they've got to find the data. And so that means they've got to be able to hash to get somewhere. And that, in some sense, that makes it start to look like a dictionary in some sense. Definitely not an array in any sense.
I think this is a comment, not a question, I'm not sure. In pandas, the approach to representing missing values was adopted from the R practice. NumPy nans are used to represent missings.
Yeah, okay, but yes, but that's a pandas data. A pandas frame like that has a field structure to it, right? And RDD is not that way, right? So that's where, like I say, a missing element is a kind of a funny thing. It's not an array, like related to the question I just answered. It's not an array, right? An RDD is not an array, whereas a pandas frame or a Spark data frame is, in some sense, an array, right? It's a two-dimensional array with fields and whatnot. But a raw RDD is not an array in that sense. So it'd be weird to see an application where elements are nans. It doesn't kind of make sense. Like I said, I can see where you can do an operation. If I have an array, it's a bunch of floating point numbers, and I divide by 0 with a mapping function. what's going to happen? Is it going to throw a runtime error? Can I expect it to return NANDs and then I have elements that are NAND? I mean, that's going to be very implementation dependent, but it's not probably a sensible way to go about handling that kind of data. You don't want to use an RDD as an array. It's going to be very inefficient. If you've got an array, you want it to be an array. So,
How do we set up Python program, some machine learning, deep learning model that is on my machine to use parallel computing capabilities? Do I just import PySpark package?
well, if you install and then import, Spark onto your laptop, right? Then it's going to be limited by your installation on your laptop, and it's not going to be very parallel. But it'd be fine maybe for working out the toy problems and debugging your syntax and getting things going. So you really want to be using a Spark installation that's on some substantial parallel piece of machinery. Or you want to be running a remote shell. Like I said, the early questions that came in about how do I get Spider going remotely? I mean, you could do that. So, but you probably don't want to be running Spark on your laptop, expecting it to somehow be invoking a remote machine to do the parallel computing. That's not really an intended configuration.
Am I audible?
Yep.
This is Brian. I just wanted to real quickly interject that this has come up a couple of times, and there's one additional aspect to this, which is going from a single machine to computing on an actual cluster for Spark. Again, there's instructions for how to do this one way in the Bridges user guide, and there are other ways to do it that are documented in the Spark documentation. It's a little bit beyond the content of this talk, but they are out there.
Do we ever allow a driver to live outside of PSC? So in the context of this slide right here, if you can see it, Brian.
Yeah. I don't think we've ever tried to make that work. I don't know why in principle it wouldn't work, except that we might have to expose some ports from compute nodes to the outside world. And that would be a complication.
All right. And what about if you have a table format for your data, and for some entries, like person names, for example, you are missing some column, phone number, for example? How will Spark handle this missing data?
Well, I mean, you got to have something in there because you can't, you're guaranteeing it that each element has the same structure. So you can't have missing, you can't have one element have 3 pieces and another have 4 if you want it to be a data frame. If you don't want it to be a data frame, that's fine. RDDs can deal with every element having a different structure to it. That's absolutely fine. What you can't have is a data frame that looks like that.
Is it possible to load HDF5 files as RDDs similar to what we do for text, images, and so on?
Say the beginning of that one more time. You got cut off. I'm sorry.
Is it possible to load HDF5 files as RDDs similar to what we do for text, images?
Yeah, oh, absolutely. Yes, yes. There's an HDF5 connector for Spark, absolutely. And it's good at reading the metadata, and it will read that into appropriate data frames. It'll do nice and transparently. You will end up with data frames that reflect that the metadata in organization of the file. Yes, it's nice the way it does it.
What is the best way to import netcdf files into an RDD? Googling turns up a number of options such as GeoSpark, Spark Array, etc.
I haven't done a netcdf file in general. I haven't touched one in a number of years now, and not in Spark probably ever, I'm almost certain. So I would do exactly what you just did, which is Google and see the best connector to do it with. And so I can Google along after the fact, and maybe we can figure out between the two of us what the best way is. But I'd have to look at the alternatives and see what the trade-offs are. I'm absolutely positive. If you'd asked me, I'd said, I'm guarantee you there's a way to do it, because like I said, Spark has a rich pool of these kind of things, and netcdf is a common enough format. But yeah, if the answer is that there's 5 different ways out there to do it, that doesn't surprise me. And I don't know what the alternatives bring to bear. So if you remain confused, let me know and I'll look, and maybe between the two of us, we can figure it out. But yeah, I can't tell you personally. I haven't gone down that route myself yet.
All right, perhaps a comment. As I understand it, the reason for using special representations of missing values like NaN is to make it easier to avoid inappropriately including them in computations.
Yes, this is true. I mean, well, it's one of the reasons. Yes. I mean, another reason is just to have an alternative to runtime crashes. But this is mostly for something like NumPy, where you're trying to do math operations on arrays or tensors for that matter in general. So if you're trying to do general tensor operations, then having a NaN come back and preventing a crash might be something that's useful to you. Spark is not intended to do, it's not intended to structure things as arrays. They're not. RDDs are not arrays. And so trying to do something like a matrix multiply with Spark, RDDs is not the kind of thing you want to do. So if you can tell me what your application is that you're specifically looking at, I'll probably give you an idea of how you'd implement things, the kind of frameworks that might be useful or interesting to you. But if you're thinking of Spark RDDs as the same functionality as NumPy arrays, they're not at all, because NumPy arrays are arrays. They are tensors. They are meant to be applied to other tensors with math operations. RDDs are not meant to be applied that way. They're scattered around memory in disorganized ways intentionally. So trying to do a matrix multiply or something like that is not the kind of thing that they do. So.
When is it preferable to use a data frame over an RDD data structure? Can you give us an example?
Yeah, sure. First of all, I mean, there's a couple of use cases. One of which is some of the algorithms they want data frames, and that's a reasonable expectation, because they say, we know that to do something meaningful, you have to give me this text string and a label or whatever. So some of the APIs really want, especially the newer ones, want data frames. So that's one compelling case right there, is when you know that your algorithms want a data frame. Another one is if you find yourself looking at all of your data and it perfectly fits, you say, I do have, names and addresses and zip codes are my RDD. That's all this RDD is. Then why wouldn't you want it to be a data frame? Just because that documents it better in the code. It brings you some of the SQL type statements now you're allowed to use, and it will help the performance. And it will cost you virtually nothing in terms of effort to do that. So if it's a natural fit, if you're naturally working with structured records, why wouldn't you? So those are, performance, just better structured code and algorithmic demands are probably the three reasons that are, going to push you there. And again, the distance between an RDD and a data frame is tiny. I hope you can see that converting between one and the other is trivial.
In sklearn, there is a function, train test split, to split data into training and target data. Is there a Spark equivalent that scales up?
Yes, indeed there is. And we will cover exactly that tomorrow with our recommender system. So yes, it's important when training supervised learning models to split your data into training and test sets. And Spark has a very convenient and sophisticated way of doing that. So we'll get to that tomorrow. Absolutely.
What is the atomic unit of RDD?
I'll interpret that as, what's it? I don't know how to interpret that. I'm not sure what that question means exactly. You'll have to elaborate a little bit more what atomic unit means in this context.
Do Bridges resources, these terminals, remain accessible after workshop?
Yes, they are accessible for the next 2 weeks, or maybe 3. If Tom is still out there, he can tell us if it's 2 or 3, but it's at least 2, and I believe it's 3.
Yeah, I think I set them to a month, but we always run out of units. So it's actually whenever we run out of units is when they get shut down.
Okay, well then, yes, we are sharing these service units, so the amount that's awarded on this grant is shared amongst all of us. So I guess in some sense that implies, please don't be a jerk and burn up the units after the workshop's done, because somebody else won't be able to do something. And if you do find yourself excited and enthused about this, please apply for a startup grant, because it's trivial. And then you have lots of units of your own to use. So nobody should be too concerned about how long things last after the workshop, because almost everybody attending the workshop, if not everybody, is eligible for a startup grant, in which case you can just continue for the next year.
Given what we've learned today, when is the, given what we learned today, when is the appropriate time to insert a physical model/algorithm if you wish to apply it to large volumes of data? In other words, can we create a large data store, a golden orb of data, and apply a physical model to this to learn more about contributions of the data that are generally not included in the model?
That question took a number of turns on me there. I'm not sure, and I'm not familiar with the term golden orb of data either, if that's a term of art. So you lost me with that question. If you want to rephrase it and try again, maybe I can take a shot at it. Otherwise, like I said, that kind of, I lost the thread of that there. So I'm sorry, I don't know what you're getting at, but I'd be delighted to give it another shot if you give it another shot.
So it seems one can run TensorFlow with Spark, but is it always more efficient to do so than just using TensorFlow? Should we worry about any overhead with Spark? Will you show us how to link Spark and TensorFlow together tomorrow?
I will. It's a good question. I will discuss it tomorrow. I won't actually step through an example of it. I will discuss it tomorrow because it's a useful thing to do. I will say that in most cases, I think it makes more sense to use Spark as a front end to pre-process the data sets, and then use your deep learning framework like TensorFlow to process them, and leave them as two separate pieces, because in most cases that's just simpler. However, it's absolutely possible to use TensorFlow within Spark. So I'll point you at that tomorrow. I'll give you just the documentation. I won't step through the example because I just think in most cases it introduces a needless complication instead of just treating the two pieces naturally. Naturally, usually Spark is a good preprocessor for the data, and then your learning framework is a good thing to take it from there. But you can embed, you can run Spark within, or TensorFlow within Spark. There are multiple ways to do it. I think I cover like 3 of them tomorrow, but just briefly, I don't dive into it too much. Now, the main reason that might seem attractive to you is potentially to do a hyperparameter search. I don't want to get too far ahead of myself, but I guess, especially because we're running out of time here. But to do a hyperparameter search within Spark might seem attractive. But these days, recently, the frameworks to do that, there are better ones just within the TensorFlow ecosystem itself. So that reason it's kind of become a little bit moot. But we'll get back into that topic tomorrow. If you want me to elaborate on it more when we've got those, that right in front of us at the time, that'll make more sense.
This is maybe a comment just to clarify, because I haven't been so clear. The kind of missing value I've been referring to is a single scalar value that might be represented as nan, null, or none, and not an array.
Okay, yeah, it's clear you've got a very specific use case in mind, which I always like, because that means I can, there are real answers to your questions. But I also have not really had occasion to worry so much about this particular topic. Like I said, in most cases, when and I've been very concerned about things that are exceptions, numerical exceptions in the past, but usually it's been in the context of an actual numerical framework like NumPy, not as an element here. So we got, if you want to email me your exact use case or an example of what you're trying to do or whatever, we can probably work through it and figure out what you're trying to do and how Spark reacts to it, or maybe if it's even platform specific, because you're stepping outside of my bounds of experience here with, like I said, worrying about nans worrying about operations that generate nans. Well, yeah, I think let's take this one offline to me directly, and we'll try and figure out if we can see what's helpful for you, because otherwise I am, like I said, at a loss as to what you're ultimately trying to accomplish.
Can you compare and contrast Spark and Dask?
Dask is you know, Sean Brown is a huge fan of Dask, and I am not experienced with it. So no, the answer is I cannot. Director of our center is very fond of it, and has used it for epidemiological modeling, as a matter of fact, in the past. But I do not. I cannot do a fair comparison of the two. I can say that it's, without having ever used it, I can say one of the reasons I've never used it, it's a niche kind of tool. So I don't know if it has any of these capabilities. I don't know. I'll take a look, since Sean would probably appreciate the next time that he asked the job interviewee, you know, how that stuff works, if somebody else in the room knew what he was talking about. So I'll take a look at it and maybe answer your question tomorrow when I come back, but I can't right now.
As you mentioned, RDD is an unstructured data. What are the elements of RDD?
Well, I mean, the elements are whatever type you read into it. So the elements can be, you know, strings or integers or tuples of any type. So the elements are, when I say unstructured, what I probably said, I hope I said, was unordered. So it's an unordered bunch of elements. The elements can be any data type that your language will accommodate.
I think that's it for questions. We got a lot of thanks from people.
Okay, well, thank you for your attention. And yeah, I regret, I've got to figure out how to get this auto scrolling to work because it's not popping up. It's just backing up the queue here on chat. I'll figure that off offline, but thanks to Steve for making sure that wasn't an impediment. We're 5 minutes past the hour already. So I will see you all tomorrow at starting time promptly, because we got a lot to cover. We're going to do something much more sophisticated tomorrow with the recommender system in the morning and with deep learning in the afternoon, building on what we've done here today. So thanks for your time and attention, and we'll see you all tomorrow.